So at first you have a design phase where the simulation is used, and based on the simulator, a design tool was developed. And then an operational plan is done, for example, how to change these modules. And this plan is then first executed on the simulation side. And if this verification step is successful, it would then be sent up to the real space system. For these projects, only ground simulators were built. So the plan was then sent to the ground simulators and executed there by the robots. And as these are quite large projects, I will mainly focus on the simulation aspect that I worked on. So why use Modelica? There are many reasons for this. One, we have a long heritage at our institute using Modelica. We have built up a number of libraries over the years. The one important one for this project was the Modelica Space Systems and Environment Library. We used this already in many previous projects, and it contains models to simulate the orbit environment as well as the satellites and actuators and sensor models. Also, we have worked for quite a long time on our robot and robot dynamics libraries. Originally, we used them for industrial robots. Perhaps you know the company KUKA. This was one of our first customers, more or less, for these libraries. But they are built quite flexible, so we can also use them for all kinds of robots and build up new robots really quickly with them. And also in our institute, we have many other libraries. Some of them are also commercial, for example, the flexible bodies libraries, the visualization library, and the optimization library that probably some of you know. And also the multi-body, also it's part of the standard library. Mr. Otter, our chairman, worked on this quite a bit in the past. So what were the challenges for the simulation? Because you have these multiple robot arms and also all these individual components, it's quite hard to model this directly in an object-oriented way in Modelica. In Modelica, typically the number of states have to remain constant for one simulation. So, for example, if you fix a module on another part, the number of states would change in reality, and for the simulation, this is not possible. Also, this is a quite complex hybrid system. So we have discrete and continuous parts. The discrete parts are mainly from the control aspects and also the logical parts that run in the background of the simulation. And as I mentioned in the beginning, these SI connectors can not only transfer mechanical loads, but also power and even thermal fluids. So many disciplines are involved for the simulation. And you have these dynamic robotic pick-and-place operation with the high numbers degrees of freedoms. For example, for the multi-arm systems, you have 15 degrees of freedom, so this is quite a complex simulation. Because the number of states have to be constant, one workaround that we often used in other problems and similar problems is to use force constraints. You probably have seen something similar before. So if a component is connected to another one, you constrain the forces such that the components are fixed together, and if they are free, you unconstrain it. The problem with this approach is this works quite nicely for a limited number of connectors, but if you have many of them, you get numerical problems, and it can even become unstable for the simulation. It also gets quite slow. So the task was, if we have many modules for one of these satellites, how can such a method still be used to have one continuous simulation without a restart, and without to have many simulations that have to be then exchanged by each other. So what I built up, I called it tensor body models. So in essence, these are rigid bodies which can change their shape and their form. And in this way, we can have a minimal number of different bodies. So we only have one tensor-shaped body for the whole satellite with all the modules, and also one of these at each end of the robot arm. And in this end, this way, we only need to use a minimal number, in this case 2 constrainable, switchable constraints for the robot. And if a module is moving an object on the satellite, then we recompute this tensor body with a new geometric shape, a new inertia. And we can also even include some simplified models for the electricity or for the fluid dynamics inside of these models, for example, for the heat exchange or for power transfer. And each of these modules also has an individual number of connectors. So not all components have a connector on each side. You can have less of this. And all this is then included inside of this tensor body model, which reduces the complexity for the simulation in the case of degrees of freedom and the number of states. So a typical pick-and-place operation that occurs for these tasks is that the robot moves to a certain position, grasps a module by switching on the SI connector, and then replaces the component to a different position, and disconnects the component there and connects it to the SI connectors of the satellite base or for the antenna base. And with regards to the tensor bodies, this means one of the elements is deleted on one of the stacks and then recreated on the robot arm. But since this is done in one event in Modelica, there's no change in mass for the complete system, so the dynamics are correct in this case. And only one workaround has to be done if no component, for example, is at the robot arm, a dummy component has to be used such that the number of states remain constant for the whole simulation. As I mentioned before, the models were quite complex. I don't have the time to go in all the details, but I want to give a short overview of what was also included in the models. The main components, as I mentioned before, are these tensor bodies that are really computed in each transfer step. We have a really detailed orbit model inside there, including the sun and the moon, which enables us to have surface heat models for these bodies. They are also dynamically updated when the shape is changing of the module stack. And we can, for example, include albedo radiation, solar radiation, and so on as a main heat source in space. Also included is a surface contact model, which changed with the shape of the tensor body, which enables us to detect collisions. This is especially important because other partners in this project, for example, worked on a trajectory generation algorithm. So the simulation can then tell if a collision occurs and if the plan has to be redone. Also included is a simplified GNC system for the satellite base, and also really detailed robot models with detailed powertrain models that include nonlinear joint friction, nonlinear joints with friction, and also position and torque controllers on a joint level. As I was only responsible for the simulation part, there was also a UDP interface for other project partners to connect to the simulation. The main part that connected to the simulation was a Cartesian robot controller, which was done by our sister institute, Mechatronics and Robotics. This is a high-level controller which works in a slower rate than the joint controllers, which are included in the simulation, and it commands the robot on a Cartesian basis. And this controller is then giving a trajectory planned by another project partner, which commands the robot in a Cartesian space. The mirror project, as showed at the start, is still ongoing. There were some delays. The MOSA project is already finished, and I showed some results for this. So the demo scenario was to reassemble a modular satellite. You can see the picture on the top left. So this was the ground simulator where it was executed with only a number of modules to simplify the simulation and also the whole build-up. And as I mentioned, the simulator was first used, and then the complete plan was transferred to the real system. And because the interfaces were designed such that the real system and the simulator had the same interfaces, this exchange was quite simple. Now, video for the MOSA project, you can see the trajectory is speed up as my testing for trajectory, so it's a little bit faster than it would be in reality. But you can see how the robot can pick up individual components and place them at another part. And you can also see from the colors if a component has power. So the green component would be a power plant module, and only if it is connected with a correct with the connectors to a system, then these connected parts are powered. You can also see the heat flow, but because the simulation is quite fast and nothing really changed. So the balls in the middle are the temperature of the components, and they change if they have a connection to other components. Other video is for the Miro project. This is the multi-arm robot. It's the same principle. So the multi-arm robot can use one of its arms or even its torso to locate on components. Here the weight of the satellite is much lower than in reality, but you can see the physical effects of the robot is moving, then also the base is moving. So with this Tensor body components, this is physically correctly done. And you have the advantage that you have much less states than if you would model each of the components individually. So I come to the conclusion. I showed you the results of these projects. When there are some drawbacks using the systems, you have to do some approximations. Especially if you connect something, you always assume an ideal connection. So the components are located perfectly at the target location. But this is the price to pay to have a constant number of states. And also the heat flow and the thermal operations are only approximated within the components. There's a little bit of hope that with advantage with new extensions, for example, for the Modelica language or languages like Molia, have such structural change could also be directly implemented in the language, but we will have to see if this can be done in the future. I just want to give also acknowledgements for the project partners. There were two quite large projects, so there are many companies involved. Especially GMV has done the trajectory planning, and Space Applications has done the robotic construction, and many other companies were also involved in the development of the parts and or the design of the systems. So thank you for your attention, and if you have any questions, I will answer them if I can. Yeah, and there's a little bit more in the paper. I had to make a compromise because this was work done in project, so they don't want to see everything published. So it's a little bit of compromise, but if you look in the paper, you see some more details. And in effect, it's not so difficult. You more or less compute a new rigid body each time the components change. So in the paper, I have some pseudocode where you can see how it's computed. I left out some parts, as I said, as a compromise with the project.
Okay, so next we have Megan, Dr. Megan from she's from the ECSC department in RPI, and the floor is on you.
All right, hi everybody. This is our work on extending a multi-copter analysis tool using Modelica and FMI so that we can conduct integrated aerodynamic and integrated aerodynamic and electrical drivetrain design. So distribution electric propulsion has enabled the development of electric vertical takeoff and landing, or eVTOL systems. When we're modeling these systems, we have to make multi-domain models to test our design concepts prior to building a physical prototype. Having these simulation-based studies available to us saves time and money in the development lifecycle. Having specialized tools, however, building these multi-domain models requires us to use specialized design tools that focus only on specific domains. This creates difficulties in integrated system design. However, the functional mock-up interface, or FMI, allows us to integrate models that don't exist in these domain-specific tools, expanding the capabilities of these softwares. So here we're looking at how we can use the Rensselaer Multicopter Analysis Code, or RMAC. This is developed in MATLAB and Simulink, and we extend this to support FMI using models that we developed in Modelica to perform electrified drivetrain models that we developed in Modelica to perform integrated eVTOL analysis. So here is our eVTOL model. We scaled this model from a 1,200-pound quadcopter that's in the, it's a reference quadcopter in the lab at MOO that our collaborators use. It's a 300-pound quadcopter. The rotors are 4 feet in diameter, and we parameterize all of the motors in our drivetrains using the 12-kilowatt Hacker motor. Because we want to look at the electrical domain and understand how our electrical design affects system dynamics, we want to study our eVTOL system with 2 different power system architectures. So first, we consider one architecture where we have a centralized battery. All of the drivetrains are connected to one power source. Yep.
I just can't see it in the meeting. They cannot see your slide.
Oh.
Are you sharing? I can see it in the meeting now.
Okay, perfect. All right, where was I? Okay, so we wanted to conduct analysis on the electrical domain and electrical system of our eVTOL. So we study our power system with 2 different architectures. So first, we look at the system with a centralized battery. We have 1 battery powering all 4 drivetrains. And then we split that battery's capacity into 4 and study the system with a distributed architecture. So now each drivetrain has its own power source. This allows us to study the performance of the battery and how the electrical system configuration is affected by the eVTOL system's aerodynamics. So going inside, we have our drivetrain model. We developed this drivetrain model in Dymola using the Dassault Electrified Powertrains library. We define our inputs for the FMU in blocks A. We take data for the torque, the speed, and what direction we want to turn our motors in. This comes from the RMAC toolbox. Then we also have our FMU outputs of torque, speed, and motor current to feed into RMAC so that we can compute the aerodynamics. Inside of our powertrain, we have our controller, our modulation method, our inverter, and our machine. These are all replaceable models so that we can look at our model at different levels of modeling fidelity. We also have electrical connections in block G, allowing us to connect our model to a battery model to perform more in-depth analysis on the power system source. And we also have an inertia in our model as well. So by having these replaceable components, we can model our drivetrain at different levels of fidelity with different model variants, easily switching them out so we can have one model to keep reusing it. So like I said before, we have all these replaceable models. So for one example that we have our machine models that we model at 4 different levels of modeling fidelity. So in the eVTOL community, they typically represent their motors using something like the top right. We have a voltage command with a resistance and inductance that then is connected to an EMF to provide torque to the system to provide lift. This model is very simple. It's useful in preliminary studies, but it limits the ability to perform integrated design of both aerodynamic and the electrical domains. Make this model more detailed by considering a brushless DC motor with a trapezoidal back EMF. This now takes a 3-phase signal into the motor, provides a trapezoidal back EMF that then is dependent on the speed and positioning of the motor. This switching behavior is caused by the switching of the transistors that's connected to the motor. We also consider a 4th model variant, which just uses an averaged EMF, which would be the RMS of our trapezoidal EMF. And this is our most detailed model in our study. As I previously said, we also have replaceable models for our controller, inverter, and modulation method. However, these models are dependent on which motor we select. So if we want to use our simplified motor, we just have averaged inverter models with a feed-through controller. If we want to use our trapezoidal motor, we'll use a more complex power electronic component and more complex modulation methods. So we'll have a PWM signal coming from our controller that then controls the switching in our three-phase converter that then provides the actual trapezoidal back EMF in our motor. We model the power source for the system. In the eVTOL community, they've previously modeled all of the power sources using just a constant voltage source to represent the battery. However, in real life, this is not the case. So we consider modeling our battery as an open circuit voltage or OCV battery. This is based off of the Sanyo 18650 lithium-ion battery. So the voltage in this battery model is determined as a function of the impedance. These impedance values are determined based off of lookup tables that were conducted, where the values were collected from different experiments conducted on this battery. So the voltage and all of these impedance values will change as a function of temperature, state of charge, and current draw from the battery. We have our battery model that was developed in Daimola. We use the DISO battery library. So it uses both the electrical and thermal domain. So in A, we have our electrical connections that connect us to our electrified drivetrain. We also have a thermal connection in B with both our thermal housing model and a connection to consider thermal models in the future. In C, we have our electrical scaling component, and in D, we have our thermal scaling component. Our battery model, like I showed previously, was in E. This is where we get that RC circuit, and that's connected to all the lookup tables, and then we have data connections for analysis of the battery in F. So we have all of our models that were developed in Daimola, and we want to connect it to RMAC. So RMAC stands for Rensselaer Multicopter Analysis Code. This contains all of the models for the vehicle dynamics and rotor aerodynamics. This is a domain-specific tool meant for aerodynamic analysis. It uses blade element theory coupled to 10-state Peters hub dynamic inflow on each rotor to evaluate the loads on each rotor hub. The rotor forces and moments are summed along each hub, along with fuselage drag and gravity at the vehicle's center of gravity to determine the acceleration. And this is a 6-degree of freedom linear model that's obtained via perturbation about hover with high frequency rotor states eliminated through static condensation. We have RMAC that's in Simulink, and we take our FMU from Daimola, import it, and we connect the two using the functional mockup interface or FMI. So FMI is an open interface standard for model exchange between different tools. This is really useful for large-scale multi-domain analysis, allowing us to use both the functionalities of Daimola with their domain-specific tool. So there's two main approaches with FMUs. First, we can export one model from one tool and import it into another tool using our new tools solver, or we can co-simulate models between different tools using our original tools solver to simulate. Here, we're using the first option. So we import our model from Daimola into Simulink using FMI. Our FMU inputs for our drivetrain is the desired speed command, our rotation direction, as well as an aerodynamic torque that comes from RMAC. And our FMU outputs is our speed of our motor that is then coupled to RMAC so that we can compute all of the aerodynamic forces of the vehicle. So after we couple all of these tools together, we look at how we can consider different model variants and look at how the electrical domain is affected by these different model variants. So we consider 3 different cases for the battery for 2 different model variants, or 2 different power system architectures. So we have a centralized battery architecture and a distributed battery architecture. We look at using an ideal 60-volt source so that the voltage will stay constant. This is what has been previously used in the eVTOL community. And then we also look at applying a maneuver using a more realistic battery model at both 100% state of charge and 30% state of charge. So at the beginning of a mission and at the end of the mission. So here we apply a pitch command to observe the closed loop dynamic behavior for all 6 cases. So first we look at the speed response of our 6 cases. All of our drivetrains produce the same dynamic response. showing that the power system configuration and modeling fidelity has little effect on the aerodynamic response of the system. However, if we then look at the electrical characteristics of the system, we get a different case. So first, we look at the motor current. Because the voltage is going to change between the battery cases, whether we're using an ideal source or applying this maneuver at the beginning or end of a mission, we'll have a different current draw. In a centralized configuration, our current spikes that we see here when we're applying in the first 15 seconds, when we're applying this pitch command, they'll cancel each other out because they're all connected to the same source. However, when we have a distributed configuration, all of these sources are now independent, and these spikes will now only directly affect that battery. This would require us to do further sizing analysis on the system and size the battery according to the worst case scenario, according to the current spikes. Looking, so for, like I said before, the battery current will be, those spikes that we saw on each motor will be canceled out after looking at the battery's point of view in a centralized configuration. The pitch command in this case wouldn't be a limiting factor on the system, and we wouldn't have to size it accordingly. However, in the distributed configuration, we would. Looking at the battery voltage, we see a similar case. The reason why our current draw is different between each of the two is we're achieving the same power command. However, so while all the motors have the same speed response to the pitch command, the battery voltage differs. So we have our ideal power source that will stay at a constant 60 volts for the entire simulation. When we are applying this command at the beginning of the simulation, or at the beginning of the, applying this maneuver at the beginning of a flight, we're starting at about 56 volts. If we have a centralized configuration, we won't have any ripple in the voltage. If we do, if we have a distributed configuration, we will get this ripple voltage. Same case with the 30% state of charge. Again, this shows just why we would have to size our battery to account for the worst case scenario. In conclusion, the purpose of the FMI standard is to enable model portability and reusability. In the eVTOL field, we can now integrate multi-domain models with both existing aerodynamic tools for expanded model analysis. We don't have to require these researchers to rebuild their tools. We can just integrate our models easily through FMI. So this allows us to just build one model and utilize it for analysis in many tools. This proposed approach provides simulation results that enable a new understanding of trade-offs between various model configurations and architectures. So previously, the eVTOL community didn't do that much work on the electrical domain when looking at dynamic response, but the FMI standard enables simulation with domain-specific tools, expanding our capabilities for analysis in broader applications, such as looking at the power system architecture and its effect on system dynamics. So I just want to thank, this work has all been in collaboration with the funding support of NASA and Boeing's charitable partnership with RPI. And I also wanted to thank our contributors in the MOVE Lab, so Dr. Farhan Gandhi and Dr. Robert Emick for collaborating with us. Okay, that's all I have. If it's possible to validate with experimental data. So the battery models were all validated against that's how the battery models are parameterized. They run these experiments on the battery so then we can get a good idea of what the impedances look like. In the future, we could, if we had access to I don't have access to the test bed, but if we did have access to the test bed, we could collect data from the system and compare that to our models. So yeah. The method for FMI? We're model exchange. Yeah. With what? What do you mean? Yeah, we're using FMI toolbox from RMAC.
Okay, so the next speaker is Hubertus from Model. I think you already got into this in the previous presentation. And
okay, thank you very much. I am actually presenting for colleagues. This one doesn't work, so I have to do it here. But also fine.
So I'm here only as a presenter. All the work was done by others. I hope I understand enough of this to do this. This was work by my colleague Clément Quick. He's French with two French professors from different institutes which work with aerospace applications. It's very related to Megan's presentation, but it's work that you would typically do much earlier in the design cycle. So what is this about? It's a use case figuring out an optimal drone architecture for a very specific mission or use case. And I will talk about the drone model. What are the model choices? The propeller model as one example. So this paper is really more about the optimization method. So I won't talk about everything in this and the sizing scenarios. And then the optimization that we perform with the problem statement solving and implementation and results. The interesting part here is that we do something that is usually done separately in one go, meaning we're doing sizing in combination with finding an optimal trajectory. And this is interesting. We usually do that actually in other industries. We do that quite often in energy, where you know complex trajectories, let's say energy demand loads for a microgrid, and you need to compute at the same time as you compute these trajectories that you want to control in an optimal manner in terms of the system that takes care of the loads. And at the same time, you need to determine the sizing of storage. So where we use this most is sizing of storage, but this is a different case where we actually look at physical parameters of the system. So let's look at the case study. Or actually, I do this, yeah. So, the case study is payload lifting. People are thinking about replacing cranes at the very end stage of a building project, because the cranes are very expensive to rent. So what you can do instead is that you use small drones to lift smaller payloads into the building. In this particular case, we say the maximum weight is 25 kilograms of the payload, and we want to achieve 150 climbs of 10 meters height within 10 seconds of hovering in with one charge of the battery. The drone architecture that we selected for this has 4 fixed pitch propellers, 4 outrunner brushless motors, 4 electric speed controllers, mainly made from MOSFET converters, 1 battery, so 1 central battery of lithium-ion cells, and 1 mechanical structure frame consisting of 4 arms and 1 central body. But what we are looking at really is variable sizing. So we look at potentially different propeller sizes, battery sizes, obviously, also that we need to make sure that the supporting structure can carry both the load of the battery, other weights that are part of the system, and obviously also the payload. So this is a somewhat unusual way of looking at optimization problems. Let's look at the drone model choices. We have 2 things that we want to do with this. One is 1D trajectory optimization, the other is component sizing. The good thing is, because we're using an A-causal language, Modelica, the sizing requires usually inverse models from simulation, but that's easy on the Modelica side. The interesting part here is that these French professors had never used Modelica before, and they are using very specialized tools where they need 2 or 3 models for doing the things which we all can do with a single model. Nobody in this room is so surprised about that. This is why we use the language. But anyways, in this case, the performance flight simulation requires direct simulation, typically in terms of equations, and the sizing inverse simulation. We're using scaling laws and meta models for sizing. That is quite common. You don't do super detailed physics, but I will go more into that, and mostly efficiency-based modeling, meaning low fidelity models. But remember, this is early in the design cycle. You would do the other steps also equally well in Modelica. So the requirement from the 1D trajectory optimization is that all equations are at least C2 continuous differentiable because the optimization algorithm requires that. That is not as hard as it sounds, but it's a little bit, you have to get used to it because the Modelica standard library does not fulfill that typically. And you can work with discontinuities if these are bounds, min and max bounds, quite well in the optimization, but you cannot work with the discrete parts of the Modelica language because that does not work with these algorithms. What you need for the design variables really that you actually use the properties of the Modelica language of min, max, and nominal, because in particular, the nominal is fundamental for being able to do proper scaling. And all these optimization problems always require proper scaling of the problem. And what you need to do as a starting position for any trajectory optimization is that you need an initial trajectory, which does not have to be optimized at all. It just needs to do something, gives you any idea of how to go from A to B. Often the simplest one is a constant input or something with a minimalistic control or anything like that. Okay, so let's now again let's look in more detail at the propeller model. And we want to get two things out of it, the physics in terms of the performance, and we need scaling laws in this in terms of the sizing. There are equations for thrust and power of propellers used here. Oops, sorry. And what you can do if you have a number of equations in a particular given problem, you can use the Buckingham Pi theorem, which people that might know thermodynamics and fluid dynamics, it's used, Reynolds number, Nusselt number, Grashof number. These thermodynamic numbers are derived through this Buckingham Pi theorem, which basically tells you if you have a number of equations and parameters in there, what is the number of really that are connected in multiple ways, what is really the number of independent ones that you can use for sizing. I see papers which actually don't always do that and figure out the best parameters, but you're using here basically dimensionless parameters that give you the right number of parameters that you can really independently size in a propeller. So these here are really beta, the pitch to diameter ratio, J, the advance ratio, and the air compressibility indicator. And with that, you can really set up a minimalistic sizing problem. What we're doing here is, in order to have a simple and fast executable model, is that some polynomial fitting on maps is done, and then these maps are really used in the combined trajectory optimization sizing. So the sizing scenarios are several different operating modes. Hover, so you're not moving, and there was a hover phase in the scenario. Takeoff, which is maximum power and increasing J ratio, you advance faster and faster through the air until you reach your final speed. And climb, which is a constant advance ratio. And what you're seeing on the right is in much more detail on the paper is really looking at the design drivers for all of the components, for the propeller, the motor, the controller, the battery, and the frame, and which of these modes actually influence the design drivers and what these design drivers are. So you have, in terms of a sizing scenario, not all modes influence all of these sizing parameters. But because we have the trajectory involved, we really look at the problem in a very holistic way. We look at the typical payload trajectory. So next, let's look at the optimization. What we want to do is we want to maximize the number of flights, or our objective is to minimize the energy consumption per flight. And you can then look at possible trajectories, how you go up there. You can do it one way or other ways, many different ways. And but we want to find the energy optimal way. And this trajectory is one of the degrees of freedom in the optimization. And what we get from there is really that we get power requirements from the trajectories, and that influence the component sizing, which influence the total mass, which influence the power requirements. So we really have a close problem where we need to solve these things in one go. And it's quite interesting. You really get very different results when you do them simultaneously as compared to sequentially. There are a number of constraints on the component sizing, obviously. That's where physical constraints hit you. And they can fortunately be included in the optimization method. So how is this done? We capture the ground model in one Modelica model with pre-sizing, mass estimation, and behavior. And then we have a small extension of Modelica called Optimica, which has been published a long time ago, 2008, and it's open. It's even been implemented in Open Modelica, I think, because it's a very minimalistic extension of Modelica. But the extension allows us to describe the optimization problem. Okay, since we are at the Modelica conference, I'm actually daring to show some real code and what this stuff here is. So this thing is the Modelica model, the drones model with pre-sizing and mass estimation behavior. And then Optimica is the optimization problem around, where we look at the design parameters, the trajectory that we want to optimize, and also what the free parameters are. So we have one equation for the objective, controllable. We have a trajectory, which is designed as an input to the simulation here. And then we have a couple of constraints, which could be equality constraints or inequality constraints. And then we have an optimization attribute. This is one change to the Modelica language. For the parameters, we can say free equals true, which is different to fixed equals to false, because it tells the optimization that this is a parameter that you can change during the optimization process. Yeah. Not talking about initial values. So if we look at optimization results, we looked at two different ones. One where we just look at trajectory optimization, and one where we use a trajectory and design optimization. And that you can see that you actually can get quite separate, different results. And it's fairly difficult to try to solve that sequentially in an equally good way. What came out of that is a drone that is about 45 kilograms, 27 kilograms of which is battery, plus 25 kilograms payload. So the difference between the 27 and 45 is the mass of the drone, which captures the propellers and etc. So I think, I'm not sure whether there are any experts in this. I'm actually not able to explain the results of this very well. What I think is more interesting is that there are really many other domains in which you could use the same type of approach with good results. Ones that I came up with is, for example, delivery vehicles, automotive ones with fairly fixed missions, or mining vehicles or vehicles for, let's say, logistics centers and hubs, which have very predictable missions, that they do, and electrical loading, you could do really the same thing. And then in energy as an industry, co-sizing of storage with operations. And I see also in HVAC as you can do co-design between building and equipment, and in particular sizing of storages, like potential cold storage in buildings. They would all benefit from this co-design of how do you operate the system once it is built, how do you design the system before you go in, where this co-design of controls or how you run the system and the sizing really gets you much better energy optimal solutions. I should say that we are using a different backend and framework than is used in other Modelica tools. I think OpenModelica had a prototype for that at some point. We're not using FMI for our transit simulation. In Model on Impact, we're using FMI, but this is basically an interpretive model where we transfer the Modelica equations into Casadi, which is a framework for automatic differentiation, and written in C++. So we have this whole system in memory and evaluated, and Casadi computes first and second derivatives so that you even get Hessian matrices. Some conclusions and perspectives. This came about because the professors in here are working with a very specialized domain-specific tool called Fast OAD. I don't remember what it is for, but it's on GitHub. It is based on OpenMDAO, which is an MDAO stands for Multidisciplinary Analysis and Optimization. That's the aerospace industry term for trying to do what I just did, in this engineering problem. It is in Python. You can work actually with FMUs in that. So you can use PyFMI and or another FMI integrator, integrate it into Python and use those optimizations. But it's not as flexible because in an FMU, you cannot optimize parameters anymore, right? That's fixed. In this other code, Fast OAD, they need a separate model, especially extra coded for the initialization problem. They can't use the same model as we can use. And that was so the causality was also very useful in terms of getting this done. There's a torque trajectory optimization that was fed with an initial position control trajectory, and that was simulated from the same model. So we use a position control for starting an optimization that does a torque optimization. One important feature in terms of making these things really work, everything needs to be normalized. It's very important that you work with variables that run between 0 and 1. That makes convergence much easier in these kind of problems. And one of the big advantages is that the derivatives at the hand of the optimizer, so these problems solve actually really fast. It was 30 seconds compared to 2 minutes. Typically, I see much higher, much faster if you compare a trajectory optimization based on the method that we have in Optimica, which, I don't go into all the math behind it, but it's different than solving time trajectories. We solve for the whole trajectory, discretized trajectory at once, where every element in the trajectory is represented by a polynomial of some order that is choosable by the method. Okay, I think it's not all black and white. These and the other model, they allow to integrate also CFD models and do large-scale things that take very much longer. But I think early in the design cycle, these methods are much faster. They allow you to do much faster iterations and get the results. You basically don't need to wait for optimizations here. It's almost immediate. All right. So quick recapture. We did simultaneous one drone 1D trajectory optimization and sizing. It was done in Model on Impact. We use scaling law-based sizing and efficiency-based performance models. And results obtained with this domain-specific tool and Model on Impact were similar. But this Optimica-based method was a much lower threshold for Modelica engineer, but the model requires a little bit of preparation in the sense that you need to make sure that the equations are differentiable. So yeah, the drone is a simple 6-degree of freedom drone, but with regulatory constraints. Thank you.